All right. Hey, everyone. Welcome to our talk. In the next 30 minutes, we'll walk you through how we are building a scalable compute platform all the way from bare metal to apps. We are part of the central compute team at LinkedIn, serving thousands of engineers. We don't use Kubernetes in the traditional way, but we extend it extremely heavily. Just a little warning, we'll have a bunch of slides, bunch of text, and bunch of pictures. Feel free to take snapshots, and we'll share slides towards the end as well. All right. Before we get started, a little bit about us. I'm Ronak. I'm based out of Toronto. This is my third KubeCon, first one as a speaker, and 2022 Detroit was my first one. Outside of Kubernetes, I love to play racket sports, specifically badminton, if someone wants to play. And I also host a podcast called Software Misadventures.
Yeah, I'm one of the top followers of Ronak's podcast. Hello, everyone. My name is Ahmet. I'm coming here from Seattle. I think this is my 7th or 8th KubeCon. I couldn't count. I think this is my 3rd time giving a talk. Outside Kubernetes, I like gardening and houseplants, but actually still outside Kubernetes, I like to develop kubectl plugins for you. Maybe you're using a few of them. So I want to walk you through LinkedIn scale, because without putting things in perspective, I don't think you'll get a full picture of why we're building what we're building. First of all, I assume you're all familiar with LinkedIn. We have over 1 billion members on our site. And these members are served by some 3,000 services. And some of these are databases, stream processing services, or microservices. And these systems run on about 500,000 plus servers. And these servers are, again, a mix of Kubernetes as well as our in-house orchestrator. And these applications run on 1.5 million containers. It's a pretty good number, and they all get deployed pretty frequently. We're serving thousands of engineers internally at LinkedIn, and they're doing deploys multiple times a day on these applications. And one interesting thing about us is that we do not run on a cloud provider. We have our own data centers, and we run everything on bare metal. We do not do virtualization for many reasons, one of them being performance. So today we'll walk you through our compute platform. You'll see 3 layers. At the bottom, we have an infrastructure as a service layer. You're not going to see any Kubernetes in that box. And on top of that, we have a Kubernetes cluster management layer, which are the concepts that you're kind of familiar with. You know, there are clusters, pools, nodes, that kind of stuff. And we'll talk a little bit about some of the controllers that we built there. And on top, most of the talk, we're going to dedicate this talk to the workload platform layer. But first, let's start with the bottom 2 layers. So I'm going to cover these one by one. I want to start with the infrastructure as a service layer, and then move on to the Kubernetes cluster management. So in this case, in the infrastructure as a service layer, you saw a few boxes, and let's go through them one by one. First, we have an inventory manager. You can think of the inventory manager as a metadata store of which machines we have in our data centers. So for example, if a data center technician comes into the data center and racks a machine in, well, that machine has to show up in a database for us to use. And that's the machine name, what are the characteristics, what is the hardware, what's the CPU, memory, GPU, that kind of stuff. And on top of that, we have this component called Compute Broker. Compute Broker is basically kind of like the heart and brain of our data center and machine layer. It's a centralized component that everyone talks to. It's not a Kubernetes operator. It's actually just a gRPC service. It's a pretty simple one. It helps you manage the pools and remove capacity to the pools. If you're using a cloud provider, you can think of it as your virtual machine scale set or auto-scaling instance group API and so on and so forth. So the pools that we have are composed of heterogeneous hardware. We don't really get fixated on like specific machine types and so on, but these machine types are largely interchangeable within a pool. And we'll talk a little bit about this shortly. So each pool specifies something called a node profile, which is basically what do you want out of a machine, and we kind of capture these minimum requirements as the lowest common denominator to configure a pool. And the compute broker itself is also the source of truth for machine allocation and maintenance operations. Like if a machine belongs to a pool, Compute Broker is basically the database for that. And if I, let's say, want to take a machine out for maintenance, or if I want to, change the hardware on that machine, I come to the Compute Broker to schedule a maintenance operation. And lastly, we have host health remediation. Well, it turns out if you have that many machines, some machines are always going to be failing in your data centers. So we have built automated systems to take machines out of rotation, service them, do upgrades on them, and so on and so forth. So the maintenance orchestrator that we built actually has some decent ideas from Kubernetes itself. It's an orchestrator that goes through our fleet and upgrades our fleet. Because again, when you run bare metal, you have to worry about kernel upgrades, security upgrades, and so on. So the first concept that I'll talk about in the maintenance domain is the concept of maintenance zones. These are not like your availability zones. They're actually just software update domains for us. So when we roll out a software update, like a kernel upgrade through our fleet, we stripe our data center to 20 different parts. We call them maintenance zone 1 to 3 all the way to 20, and we roll these software updates out one by one. By doing so, we kind of ensure that we're not taking more than, let's say, 5% of the capacity in a particular data center out at a time. So if we have a bad kernel that goes out and somehow the machines don't come back online, we only take down 5% of the fleet that we have. Now, the compute pools that we create that runs our applications, the pools themselves have machines participating from each of these maintenance zones. And so when you look at a pool, it's striped evenly across our data center. However, that said, the Kubernetes clusters themselves are still very much a fault domain, right? When you deploy a bad operator or when you mess up your webhook configuration, you're kind of breaking that entire cluster. So there's that. I want to talk a little bit about the coordinated maintenance operations that we have. So as I mentioned earlier, humans are not in the loop for doing maintenance in our fleet. All our systems are rather automated. If something goes wrong, again, the systems talk to each other to figure out what they need to do. So we have this concept of a disruption. Disruption basically means you want to take the control from Kubernetes or whoever is using that machine away from that person and give it to a maintenance actor. So we have two types of disruptions in our fleet. One of them is planned maintenance operations. This is basically your regular OS kernel upgrades, your switch upgrades that are happening in your racks, hardware decommissioning operations that we have, or maybe the kubelet upgrades themselves as well. And the unplanned operations, as you can imagine, they're when stuff goes really wrong and we need to get this machine out of the way. So these are usually the host health remediation operations. So this picture kind of shows you what happens when we receive a disruption. So in this case, you have several actors. A machine disruptor comes in, creates a disruption, and this disruption gets sent to the compute broker. So now compute broker knows about this disruption, and our cluster management layer observes that, okay, somebody wants to take this node away, let me cordon drain the node, and we approve the disruption, we give a thumbs up. The maintenance actor sees that, it does its thing, but whatever it needs to do, either reboot the machine, reimage, whatever it needs to do, and then they remove the disruption, and then we put the machine back in rotation. So all that is automated. Now, I want to talk a little bit about how we organize our Kubernetes clusters. I bet you're all kind of curious about that. We don't use any specific Kubernetes distro. We just take the open source bits, we configure them in our own way. We don't use any kubeatom or cluster API. A lot of the features in cluster API are actually stuff that we don't need. We use a single provisioner. We don't run on cloud providers and so on. So our stack is pretty simplistic in this regard, and we want to keep it simple. So this works well with our cluster bootstrapping stack. We also tune a lot of flags in API server and etcd. In terms of cluster size, which I assume is a hot topic, we like to push our clusters to 5K, and we want to actually push them a little further. And the main motivator behind that is to reduce the hardware fragmentation across clusters. Like if I need certain hardware used by a certain customer, I want to kind of keep it all in the same place. And another reason is we want to do that is clusters are multi-tenant, and customers grow in place. You deploy an app to a cluster, well, we want to give it a little bit of a wiggle room to grow, and our clusters are pretty mixed up. We run stateless, stateful, batch workloads all in the same cluster. And the kubelet upgrades that we have in our fleet, again, as I covered earlier, they happen as part of the OS maintenance. We regularly upgrade kubelet itself. And we have a centralized hub cluster to manage all the other clusters that we have and manage which application goes where, which Ronak is going to talk a little bit shortly. So we use the Kubernetes resource management concept. We use the KRM APIs. We've built our in-house controllers to manage the pools and clusters that we have. Here's a pretty simple example. We modeled the Kubernetes pools as a custom resource in our management cluster. And these changes, portion of them gets converted into a compute broker custom resource, and then the compute broker pool gets synchronized to the gRPC API that compute broker offers that I mentioned earlier. However, we use this custom resource to specify other like Kubernetes-related settings. For example, what daemon sets do I have? What node labels do I have, right? And when you model things this way, adjusting capacity on a pool becomes really easy. You just change an integer on a YAML file, you submit it, and then you wait for a minute, and suddenly you have bare metal machines showing up in your cluster. Pretty magical. I want to touch on how we scale Kubernetes itself. As I mentioned, we were running pretty large clusters, and the clusters, the control planes themselves are shared resources technically. If your control plane goes down, well, it's bad time for basically everybody, right? So when our customers bring their own operators into our ecosystem. We heavily review their RBACs so we can kind of control what they can and cannot do. And on top of that, we use the APF, which is API priority and fairness, to ensure everyone is kind of staying within their limits. Now, etcd is a hard topic. Again, etcd doesn't have a lot of these like cool mechanisms to restrict load. And etcd also happens to be the first bottleneck when you try to grow your clusters. As you submit more events, there's more pod churn and all that, like your etcd will get overloaded. So one thing that we've done is we've increased etcd storage limit from 8 gigs to 16 gigs, and we're planning to potentially increase it further. We run etcd on SSDs, so based on our stress testing, this seems to be okay. And we also built our internal etcd backup restore system, so in case something goes catastrophically wrong, we are going to resort to that. And controller scalability also remains to be an active topic that we're trying to figure out, because controllers, we run many of them, and you can't infinitely scale controllers. Actually, funny enough, right now there's another talk happening elsewhere about horizontal controller scaling, and it's not our sole problem right now. So this bothers us quite a bit, and we're working on it. And I'll pass it to Ronak to talk about workload platforms.
So for the rest of the talk, we'll focus on our workload platform layers. So we use Kubernetes to run our stateless, stateful workloads, as well as jobs. Now, we don't want our app developers to be Kubernetes experts or worry about how to craft the exact deployment spec. So what we do is we create custom resources, which we creatively named as Li deployments and Li stateful sets. So users only have access to these two custom resources when they're deploying stateless, stateful services. These are exposed to the users, and they don't have any permissions to any other native Kubernetes resources. At the same time, we also want to cater to other platform teams like Spark, machine learning infrastructure teams, who want to build their own platform on top of Kubernetes. So we also support those teams by providing Volcano as a batch scheduler to help with things like fair scheduling, gang scheduling. And we have built our own regional job queue as well as quota systems. The reason we built our own is because the systems that exist in Volcano today, they are cluster scoped, whereas we have hundreds of clusters running within a region, and we need quotas to be effective across all of those. For the rest of the talk, we'll focus more on how we run services on Kubernetes. Now, about a decade ago, LinkedIn started building its own container runtime and a scheduler. This is before Docker and Kubernetes days. We have been running all of our stateless and stateful applications on top of that system, and it has been serving us pretty well so far. For the last few years, we started migration to Kubernetes, and we want to do this migration without any downtime to the live site. We want to do this centrally with automation, with almost no user involvement, and at least for the stateless applications. And we want to challenge legacy requirements as we go ahead so that we can reduce tech debt along the way. At this point, we have more than half our stateless fleet running on Kubernetes, and we have several stateful systems running in production on Kubernetes as well. Now, before we go into how we run these services on Kubernetes, it's important to talk about our internal service infrastructure. At LinkedIn, we don't use several Kubernetes features like services, DNS, configs and secret management, or network policies, and the reasons are twofold. One, these features work really well within the boundary of a single cluster. But when you span across hundreds of clusters, the overhead becomes really large. For example, making Kubernetes services work across all of these cluster boundaries becomes complicated really fast. The other thing is we have an equivalent of all of these offerings at LinkedIn, which have been scaled to all of our regions, and they have been hardened over the years. So we have been developing these offerings independent to Kubernetes, and then we integrate Kubernetes with it to run our applications on top. So Kubernetes becomes the primary pod orchestrator for us. And we don't use several of these Kubernetes features that I mentioned. But we really appreciate the flexibility that it offers so that we can extend Kubernetes for our use cases. Now, let's first talk about stateful on Kubernetes. It's been an ongoing meme that Kubernetes does not really work for stateful systems, especially the ones that store data on local disk. Now, we have several data systems like Kafka. Some of you might have heard of that, Espresso, Venice, Pinot, et cetera. All of these systems store data on local disk, and we do local disk because of performance reasons. These systems are replicated, they're sharded, so any pod eviction or update requires coordination. Simple PDBs or stateful sets don't quite cut it. At the same time, we don't want to ask all of our data systems, teams running data systems, to learn Kubernetes and write Kubernetes controllers. So what we did instead is build a generic stateful controller that integrates with shard managers that teams rely on. Now, stateful teams are really good at managing data systems. They know how to build these shard managers. Our controller interacts with these shard managers through our custom protocol and handles things like pod updates, version updates, and even eviction and the maintenance aspects that Ahmet mentioned earlier. We gave a talk on how we built this operator last year in KubeCon North America, and we also published a blog post. We highly encourage you to check that out to learn more. Let's talk about stateless on Kubernetes. So for stateless on Kubernetes, a user would typically specify their simple spec in 10 lines for the LI deployment custom resource that we have. We also offer various pod orchestration capabilities in it, like Canary, for instance, where you can say, I want to ramp a change only up to 10%, validate that it looks good, and then go forward. We use clone-set under the hood instead of deployments because clone-set offers volume claim templates so that we can use a PVC per pod, which you cannot do with deployments. And then we translate this clone-set to about a 500+ line of pod spec. We rely on init containers pretty heavily to integrate with the rest of our infrastructure. We create default volume mounts, environment variables, so that an application can get everything it needs to run in Kubernetes without having to worry too much about changing it, going from our legacy system onto the new stack. Let's go through a few user workflows. The first thing that an app developer does at LinkedIn is they would write their own manifest. They would check it into their repo. As part of our build process, we also publish these Helm charts in the Helm repo. Now, because we are serving several thousand engineers, we want to focus a lot more on validation and prevent people from making mistakes even before the code is checked into production. So what happens is when you have a PR, and let's say you don't specify a field that is mandatory in the manifest, we have a GitHub action that would call out saying, hey, you're missing memory there, for example, and it'll block the PR from getting merged. There are several such checks which run, and beyond schema checks, what we also do is we have similar checks that we do in our webhooks. We run them on the PRs themselves. So even before the request hits the API server, you already see in your PR what are all the things that you're going to be blocked by. This has resulted in significant reduction of user support load for us, because now users can see what's wrong and they can go and fix it. We use a namespace per application. The reason we do that is because all of our permissions are based on namespaces, and a user only has access to namespaces which has applications that they own. If a namespace for an application does not exist, what we do is we create for the first time, and we route that to a cluster. So let's walk through this workflow for a second. A user will never be requesting a namespace. They don't even know about namespaces. They don't need to know about it. They go to our deployment orchestration service, and they'll say, I want to deploy my application. If we get to know that the namespace does not exist for this app, we get information like what is the app name, what tenant, meaning is a stateless or stateful application, and the app owners get to specify what node profile they want. So Ahmet mentioned earlier, a node profile is basically a combination of what is the machine type you want to use and hardware configuration you want to run on. So we get that information. We have a controller at the hub, which also gets information about your authorization rules from our regional authorization service. What it'll do next is it'll find a cluster which has a pool that matches the node profile that you have, and if one doesn't exist, it'll create one, and it'll propagate the namespace as well as role bindings to that particular cluster. The next step that happens is the app getting deployed. Now, the deployment orchestration service specifies the application version, passes it to ArgoCD within the cluster. ArgoCD will sync all the manifests from the Helm repo, apply it to the API server, and then our controllers take over. Our controllers interact with all of those services mentioned above. Those are regional services deployed, and all controllers running in every cluster talk to them. And then we translate these custom resources to the pod specs that I mentioned earlier. We have several logs and events that get emitted as part of our controllers and applications. All of them make their way through Kafka to Azure Data Explorer. What we do is we create default dashboard for every application. So you could simply go to a link, type in your app name, and you get a bunch of events, logs, as well as metrics, like how much CPU memory your application is using, how many times your containers are restarting, why they're restarting, how many replicas are desired, and how many are available. So all of this is given to the app owners out of the box. A quick note on ArgoCD. So we run ArgoCD 1 per cluster, so it manages all applications within that cluster. It has served us pretty well so far while the scale was small, but what we have started to see is that as the number of objects in the cluster grows, the application sync times have been going really high. The other problem we start seeing is that as the number of replicas within an application grow, the health status sync is taking too long. And this has resulted into not the ideal user experience that we want, and it's becoming more of an operational overhead for us. So what we're doing now is we're writing our own GitOps engine, and we'll be replacing ArgoCD for majority of the app deployments. We'll still use it for some of the infra pieces, but not necessarily the end user applications. Let's talk about failures and categorizations for a second. Now, going back to, again, serving several thousand users, if we don't specify why an application rollout failed, we would be getting a lot of support requests. So what we do is, for anything that is a validation error, as soon as the manifest is attempted to be applied, we fail it right away, specifying why it's a bad manifest and why the deployment will fail. If it's a terminal error, then we fail it on the first reconciliation, specifying it's a terminal error. And if it's a transient error or an application health issue, in that case, we use progress deadline seconds. We implemented our own progress deadline seconds on top of our custom resources. What it does is that if it observes there is no progress made for a given amount of time, then it fails that deployment. In addition to failing that rollout, what we also do is we categorize what the failure is and whether it's an app issue or an infra issue. So if you see in the conditions, so what we do is all of these app categorization, they make their way to our object conditions, and we show user readable errors saying this application failed because you have 18 parts which are unhealthy on this version, and this is an app category. All of these conditions, we don't expect users to necessarily go and query every single object. So what happens is our deployment orchestration service will take all of this data and send this to the UI. So a user goes to the UI, clicks deploy fail. They actually see exactly why it failed. If they went and inspected the object in the cluster, they see the exact same thing. Now, because we have custom resources and we have application running across several hundred clusters, we don't want users to have to figure out where the app is, how to query it, how many pods to list. So we provide a kubectl plugin that application owners rely on. The semantics of the plugin are very similar to kubectl, but instead of kubectl, a user would type kubectl in, and then they would do something like get pods, get li deployments, get li stateful sets. What we do is behind the scenes, we figure out where the app is running, and we scatter gather all of the data and display it to the user. In addition to the default commands that a kubectl plugin would provide, we also have some custom things like status. So a user can type kubectl in status, my li deployment, the li deployment name. You don't see the full picture here, but on the right side, that is kind of the summary we present to the user. We say, this is the li deployment name. These are the desired specs you have, whether it's healthy or unhealthy. And if it's unhealthy, here's why. And all of this information is propagated to the user. We also have a system that runs within each region. It's watching all of these custom resources, pods, and nodes, and it collects them in a central database. We built a custom UI on top that users go to debug their applications. So instead of having to just use a CLI, a user can simply go to a UI and get a bird's eye view of everything. At the same time, that UI doesn't hit our API servers, which allows us to scale API server and control plane. It hits that internal API that we built, which is collecting all of this information. Now, we also spent a lot of time on building API guardrails. So if kubectl deleting a resource would result in an outage, then we have delete protection for it. So this includes all of our custom resources that are user-facing, every single namespace, even for admins, and custom resources that we build ourselves. We also have other protections in place to prevent users from having an incident by just fat-fingering, for example. I'm sure everyone would have had gone through a time where instead of 1,000, you pressed 10 and pressed enter, and something bad happened. So we prevent scale-down operations in one shot beyond X%. And typically, that X% relies on how big your application is. We also have an upper bound on how much max surge and canary percentage you can use so that you don't go over your quota. So what's next? So far, we have been intentionally running each application within one cluster. That's been an intentional choice to keep operational simplicity. What we want to do moving forward is federate these workloads across multiple clusters. We want to align our clusters with maintenance zones, so we get two sets of alignments. One, we don't have a single cluster failure taking down an entire application. The second part is, every rollout we do as part of data plane or control plane, it also only impacts up to 5% of an application and no more. It also allows an application to grow way beyond its cluster size, and we have several applications that would grow beyond a cluster size. It also helps with machine types getting fragmented across clusters. So let's say if I need 5 GPUs, 3 are in one cluster, 2 are in the other one, if we federate a workload, we can actually utilize all of those machines too. Now, by default, we actually allow applications to burst, so they can use more CPU if it's available on the host. While this helps with efficiency, we have found that applications that care about performance, it's not enough. It doesn't give them predictability. And it sometimes results into noisy neighbor problems. So what we are doing is we are rolling out CPU pinning for these applications. And one thing we do is we only pin physical cores. We don't pin logical cores. So it gives us more isolation than otherwise. We're also building pod CNI, IPv4-based pod IPs, where every pod gets an IPv6 address that is globally routable within our entire production regions. So still, we don't have to worry about cluster-to-cluster routing. It's all just a flat network. And kubeception. We want to run Kubernetes control plane as pods in a management cluster. This makes managing clusters super easy, especially when we have several of them in a region, and allows us to stack components, resulting in more efficiency. Let's talk about migration lessons real quick. So one thing which we have learned so far is always start early and make incremental progress. Because when you're migrating something from a decade-old legacy system to Kubernetes, there are several things that you'll find that you didn't expect to. And I'm sure we all have fair share of those learnings. One thing which we also realize is migrating the first 50% is the easiest part of the job, and the remaining 50%, like that's the long tail, which takes really long. We want to also be pragmatic about the tech debt we choose to solve, because if we chose to solve everything along the way, then we wouldn't necessarily finish the migration at all. So one example is we wanted to generate container images for each application. Instead of having and teaching every app owner about how to write Docker files, we have an automated system that actually automatically generates a Docker file, creates container images on the fly, and that's what we use. We also want to be intentional about what Kubernetes features we use and expose to the users. If we expose raw Kubernetes to users, it wouldn't necessarily work for our scale. Invest in guardrails when you're exposing APIs to users, because they would use it in every which way beyond what you would expect, and I'm sure we all have experienced that. And develop good user guides and self-serve troubleshooting. It goes a long way and reduces support load significantly. Lastly, thank you so much for coming to the talk. I think we have some time for questions, and there's a mic in the middle. And also, we have some other resources we encourage you to go and check out. Thank you so much. Right, yeah, go ahead.
Thanks a lot for the talk. I have a quick question. You mentioned that you have to tune API 7 and etcd flags. I was wondering if you had considered storing the events, the Kubernetes events, to another etcd cluster. And if you have already done that, if you went back from it, why?
Yeah, I can take that. Sorry. Yeah, I can take that one. So we do currently run separate etcd events clusters for at least one of the clusters that we have. But we're actually planning to merge it back because we are not liking having two etcds. You can't use the same disk if you're running two etcds side by side. You're not gonna get that much performance out of it. So instead, we're going the route of increasing the database size.
Okay, great. Another question I had was the operating system that you use on your bare metal boxes. Which one?
So it's all Linux. So we run just Linux. Are you asking specifically about which distribution of Linux we run?
Yeah, exactly, yeah.
We run Azure Linux.
Which one, sorry?
Azure Linux. So Azure has a Linux offering, so we run Azure Linux, yeah.
Thanks a lot.
Thank you.
Thanks for the talk. Crazy to see the scale at which Kubernetes can run. Really cool. So you are using open source technology, but we also saw a couple of in-house developments. Have you considered to make it generic and donate it to the open source community? Especially for me, the kube-adm cluster installation technology sounds really interesting. So I would like to know more about it, but I can imagine some of it is proprietary, but also maybe you would like to donate something, make it generic. What are your considerations in that?
Yeah, I would say that in the past, we considered donating parts of the stuff that we have. But for example, we developed an in-house etcd operator. But right as we were doing that an open source etcd operator effort just started. So we're trying to participate to that as much as possible. But for the most part, a lot of the cluster management stack that we have is bespoke for a reason that wouldn't widely apply. And there are actually really cool tools out there that let you do stuff like kubeception or cluster API is actually pretty good for most use cases.
Yeah.
Thanks.
So you mentioned earlier that you're using RBAC for your access control. That works pretty well in a namespace as code. But the moment you need to go beyond that, somehow you lose that fine-grained access. And I wanted to ask, do you use any other webhooks or anything else?
So we actually considered writing our own webhook for authorization. So instead of relying on Kubernetes RBAC at all, we basically have this webhook-based authorization. So far, every application lives within its own namespace. An application can also have multiple namespaces because you can say, I want a prod cluster, a test cluster, so you get 2 different namespaces with those different tags. Because we have applications bound within that namespace, the RBACs kind of work out for us, so that's not been a problem. What we do, though, is we don't necessarily treat that as source of truth. What we do is we have that regional service. So we just sync all the RBAC rules on a periodic basis, and that's how we apply permissions. But if you need to go beyond that, then yes, webhook is the way to go. We have several other webhooks for different validation checks, but not for RBAC.
Thank you.
Thanks for the talk. I wonder how you solve the ingress and interactive user access and machine-to-machine access between services.
So in our production fleet, we have flat network, meaning every machine can talk to each other, every application can talk to each other. Our service discovery system relies on that as a prerequisite. So today, every application can talk to each other, and there is MTLS and authorization in the middle, meaning you need to use your certificates or bearer tokens, and then you can only talk to a service if you have the permission to talk to that API. So in today's case, it doesn't matter whether your application is running on cluster A or cluster B, the network is flat, and they can talk to each other. The way it works is our data center network is controlled by us, and because we have control from all the way to which rack we run the machine on and how we deploy applications, we can manage some of that.
What about the interactive user access, like through the browser to these apps?
Yeah, so interactive user access in terms of production, if you're talking to an application in production, you can't connect to it directly. We use jump host, for example, but typically users are not talking to applications in production through a web UI. All of these applications we deploy, they're serving linkedin.com. We have several internal applications. To expose those, we have internal proxies that we run, but they are not Kubernetes ingress controllers. So we have a traffic team that manages regional proxies. Any application that needs to be exposed to the browser becomes a backend on this traffic proxy layer, and that's how we interact with it.
Thanks.
Hi, thanks for the great talk. So my question is related to one of the initiatives which we are trying to do in our company. So have you ever tried upgrading the Kubernetes components along with the applications which is running on top of that? Like control plane as well as data plane. So
all the time.
Yeah.
You want to take that?
I don't fully get the question, actually. You want to take that?
So just to make sure we get the question right, you're asking whether we do a Kubernetes control plane and data plane upgrades while the applications are still running?
Yeah, and some of the applications, you can assume that although it's not advisable, but application is running on control planes as well.
So none of our applications run on control planes, but we always do in-place updates for our control plane and data planes. So there are, let's just say, 2 parts to it. For data plane, it goes back to what Ahmet mentioned earlier. The maintenance train would go and deploy new kubelet versions across the board while the applications are there. So we drain the machine, upgrade the machine, bring it back into rotation. For control plane, we have our custom orchestrator right now that will go and update API server, for example, in a rolling fashion. So once we check, 10% of it looks good, it goes forward. And the applications continue running. It's like inertia. Objects in motion stay in motion. Objects at rest stay at rest. So control plane or data plane upgrades don't affect the applications at all.
Does it require downtime?
Not at all.
OK. It will be very good if you can share some links or documents the way you are doing it. That will be very helpful for us. Thank you.
Happy to chat. Thank you.
That might be a talk for North America, maybe.
Oh, yeah.
Hi, thanks for the talk. I'm curious about the freedom of your teams about scalability. So you define the namespaces for the teams, and what is the limits for the teams?
Limits in terms of?
Auto-scalability in resources, CPU, memory.
So there's no specific limit in terms, OK, the limits are defined based on 2 factors. One is how many replicas you need to serve the site, and then the app owners choose how much CPU and memory they need. Typically, what happens is we have another system, which is called auto-right sizing. So it's not reactive auto-scaling, it's proactive auto-scaling. So majority of our application owners don't have to worry about how many replicas to use. What we typically do is that we observe site traffic over time. We develop a model to see how much QPS does this specific application need to handle, what its CPU memory usage looks like. And we have a decent idea of how much QPS we expect to see next week or 2 weeks from now. that system will actually go talk to the LI deployment API here and update the replica count dynamically, and the application owners don't need to worry about that.
Okay. Do you react if there's like an overuse of the resources?
We have quota systems in place, so if, let's say, for example, an application starts using Beyond, we don't necessarily enforce it in the sense that the application is killed, but the application owner receives warnings that you're going above quota.
Thank you.
Hello, thanks for the presentation. My question more about bare metal server, the management. It is always challenging, to the bare metal server. You need to get in the right NIC card. You need to know there's the nickname, and Linux has always recommendation persistent nicknaming. And also for the disk. So I think you didn't use the SDA or SDAB naming instead of maybe WWN. I mean, it's all, you need to also automate, right? So how do you manage that kind of thing?
Yeah, I mean, we do manage them, basically. Like, we have to configure the hosts exactly the right way, but like stuff like storage, for example, we develop our own CSI drivers to be able to, allocate space for containers to use on the host. So some of that is a little bit, tamed with the help of Kubernetes, but yeah, we do have a host configuration layer. We use Puppet internally, and we use Puppet extensively to configure a lot of stuff like, several kernel settings, our packages running on the distro, so on and so forth.
But my question regarding this NIC, how do you detect, which NIC card is actually online? For example, bare metal server has multiple NIC cards, and you need to pick the right one to, add it to the cluster.
So in this case, when a machine is racked in our data centers, for example, it has one NIC associated with it, not multiple NIC cards. And I would say, we have a separate team who takes care of taking care of how machines are not just configured in our data centers, but managed over time. They would be a better experts to tell you in detail on how to do it. But typically, when a machine shows up, there's one interface attached to one NIC, and we know exactly what IP address it has.
Okay, thanks.
Hello, hi. Thanks for the great talk, and especially the scale you mentioned in terms of servers. Like currently, LinkedIn has more than 500,000 servers. So is LinkedIn managing its own data centers? And if yes, then so like LinkedIn is used globally, like all around the world. So how you guys are dealing with latency? Like you're using some CDN kind of services, or is it like you have data centers like at different locations? So this is something I'm curious to know.
So there are multiple data centers hosting all of our applications, and then there are many number of POPs or edge networks that we rely on to reduce that latency to you. So if you're, let's say, talking to LinkedIn.com, it'll go to the nearest edge site, and then it gets routed to our data centers.
Cool. Thanks. Thanks for your answer.
Awesome. I guess we'll take the last question and put it up there.
Hi, thanks for the talk. I do have a question. At some point of time, you chose to have in-house solution instead of choosing like vendor solution or also what is used in Kubernetes. At what moment do you know if it was a success, and how do you collect feedback on your own work? Because you don't have anyone doing similar stuff. So how do you know it has been the good choice, and is there occurs already that you need to change, or you come back again on your decision and choose to use Kubernetes stuff?
Yeah, I would say like we try to not, lock ourselves into a corner, and we try not to make decisions that we can't back out of. So that's pretty critical to us. So we try to experiment with other things. For most intents and purposes, anything that comes from the open source into our ecosystem, we have to be experts on that. Like, we got bit by a lot of open source components. We had incidents because of them. And so as a result, we started to become really selective and really picky. And we started to read the source code. And we started to understand, okay, well, here's an open source component. What are its failure modes? What is its scaling story? Like, how can it accommodate this size of cluster, and so on and so forth. So basically, I would say there are key areas where we are able to successfully bring in something from the open source. It does exactly what we want, and we contribute back to it. Clone set operator, for example, is a good example of that. Like, it works really well for us. But there has been several other components that we still kind of hang on to, but we're aware of their limitations, and we kind of work around them. So developing in-house also hasn't been the worst thing. I think a company of our size and our engineering culture, it's kind of reasonable for us to kind of own some of our fate, especially in key areas where financially it also makes sense.
Yeah.
Okay, thanks.
All right. Thank you so much.
Thank you.
And